Okay, in Chapter 2, Section 3, we will talk about two very fundamental concepts in vector space, basis and dimension. And just to give you an overall idea of what these are talking about, a basis really is a coordinate system for a vector space. And you can think of an example. In 3 dimensions, for instance, you have the 3 vectors I, j, k. You think of these as the coordinate vectors. And any point in 3 dimensions can be expressed in terms of its coordinates with respect to these 3 vectors I, j, and k. Now, basis is a generalization of this to an arbitrary vector space. All right, now the important thing about basis is that every basis of a vector space is the same size. That is the same number of vectors, and that number of vectors in the basis is called the dimension. So every vector space has a characteristic dimension. In 3 dimensions, we have any basis will have 3 vectors. Another important way of characterizing basis is as a maximal linear independent set. The basis is linearly independent. You can see these 3 coordinate vectors are linearly independent. And if you try to add another vector to this set, it wouldn't be linearly independent anymore. Another characterization of basis is as a minimal spanning set. Here you take this system of 3 vectors, and these 3 vectors span the 3-dimensional space. If I take out any one of them, it doesn't span anymore. All right. So I could say in summary that these are the important ideas in this section. The basis creates a coordinate system for a vector space. All bases are the same size, and the size of the basis is called the dimension. A basis is a maximal linearly independent set, and it's a minimal spanning set. Okay, so we'll go through these ideas, and we'll give proofs, and I'll try to present them step by step. All right, starting with basis. All right, the definition of basis. The basis for a vector space is a sequence of vectors that is linearly independent and spans the space. So we see the 2 important ideas of basis, both that it's a set of linearly independent vectors and that it spans the space. Now, always keep in mind this standard example of I, j, k in 3 dimensions. Now, these 3 vectors point in 3 essentially different directions. They are linearly independent, and furthermore, they do span all of 3-dimensional space. So this particular example does illustrate both aspects of the definition of basis. Now here we say a sequence of vectors. Technically, the order matters. So that point is reinforced here because a basis is a sequence. That bases are different if they contain the same element but in different orders. So we use this notation to denote basis. We use angle brackets to indicate that the order is important. So according to this definition, we have that, for instance, B1, B2, I'm sorry, beta 1, beta 2 would not be equal to beta 2, beta 1. Now, this is technically correct. But in practice, we often confuse these two bases. We don't make a distinction. But technically, these are considered as different bases. All right, here's an example in R2 of a basis, 1 minus 1 and 1, 1. Of course, it's always good to draw a picture. 1 minus 1 would be, here's my, I'll call this I and I'll call this J. 1 minus 1 is out 1, down 1 here. So that's 1 minus 1. 1, 1 would be out 1, up 1. Okay, so this is 1, 1. And this is 1 minus 1. Now you can see visually that these two vectors are linearly independent. They aren't multiples of each other. Furthermore, we can see that these two vectors do span the entire plane. For instance, if I chose this point here, I could scale this vector up and then scale this vector up from starting from here, something like that. Then I could express this point, which I identify with this vector, as a multiple of this vector plus a multiple of this vector. So geometrically, it's clear that these two vectors do span the plane. But we can give an algebraic proof as well. The algebraic proof that these two vectors are linearly independent says, suppose we try to create a linear relation among these two vectors. We can change that into a system of equations that turns out to only have the trivial solution. And we remember that if the only linear relation among vectors is the trivial relation, that means the vectors are linearly independent. You can't express any of these vectors as a combination of the others. The usual proof for spanning set is here. We want to show that any vector xy, for instance in my example here this would be xy, we want to show that any vector xy can be written as a linear combination of the vectors in my basis set. In order to determine whether we can do that, we write this equation and attempt to solve for the coefficients C1 and C2 that create the linear combination. And in fact, for any x and y, we can find C1 and C2. All right, so these are two important proofs with relation to a sequence of vectors. And this is a general way to establish whether or not a sequence of vectors is a basis. First you check if they're linearly independent, then you check whether they do in fact span the entire vector space. Okay, here's another example using the vector space of linear polynomials. Linear polynomials have this form. They have a constant term plus b times an x term. Now, it turns out that one basis is 1 plus x, 1 minus x. Now, hopefully you can see the similarity between this basis and the basis we had last time. The basis we had on the previous slide here was 1 minus 1, comma 1, 1. Now 1 plus x, that's very similar to the vector 1, 1. 1 minus x is very similar to the vector 1 minus 1. Okay. So in fact, if you do the algebra, you'll find out that the algebra that shows that this is a basis is the very same algebra that was used in the previous example. Instead of working with two-component vectors, we're working with linear polynomials. But the way it works is the same. Okay? For two-component polynomials, we had C1 times 1, 1 plus C2 times 1 minus 1. You could go through all of these steps and simply replace the polynomials with the corresponding two-component vector, and you have exactly the same proof. So try to think of polynomials in this way, that basically it's another way of writing a two-component vector, where the first component is the constant coefficient, the second component corresponds to the coefficient of x. Okay, so this example is pretty much identical to the previous example. All right, now here we have a basis for the 2 by 2 matrices. And I also want to point out that 2 by 2 matrices are very similar to, I'm going to write it this way, are very similar to the 4-dimensional vectors. Right? I write this as 1, 0, 0, 0 in a square form. Now I could instead identify this 1, 0, 0, 0 with a 4-component vector 1, 0, 0, 0. I could identify this one with a 4-component vector 1, 0, 2, 0, 0. I could identify this with 0, 0, 3, 0, and so on. Okay, so this is very much like 1, 0, 0, 0, 0, 2, 0, 0, 0, 0, 3, 0, and 0, 0, 0, 4. Don't have room to write it here, but I think you get this. Now this one, the second example of a basis, looks like 1, 0, 0, 0, 1, 2, 0, 0, 1, 2, 3, 0, and 1, 2, 3, 4. All right, you can see that these are linearly independent because any linear combination of these to make 0, the coefficient of the last one would have to be 0 because the last vector here is the only vector that has a non-zero fourth component. All right, if this component is 0, then this component would also have to be 0 similarly because this is the only remaining vector that has a non-zero component in the third coordinate, and so on. So I want to point out again that though these 2 by 2 matrices are apparently different from vectors, algebraically we deal with these 2 by 2 matrices the same way we would deal with 4-dimensional vectors. Okay. All right, here is a basis for R3. This is the basis that I've been showing. I, j, and k. You know, I has 1, 0, 0, so just draw the set of axes here. 1, 0, 0, 0, 1, 0, 0, 0, 1. I, j, k. I put hats on them to indicate their unit vectors. You can put arrows on them. There's not a significant difference between those two notations. And let's generalize this notion. Now, it's hard to visualize n-dimensional space, but we can write down a set of n vectors. The first vector has a 1 in the first component and zeros elsewhere. The second vector has a 1 in the second component and zeros elsewhere, and so on. Notice parenthetically that if you write these set of vectors as a matrix, this looks just like the identity matrix. And that will come into play later. So this set of vectors that has this nice form is called the standard or natural basis. And we use the letters E to denote these vectors. Checking that En is a basis is routine. We have to check, again, we have to check linearly independence. And you have to check also that it's a spanning set. Okay, I'll leave that as an exercise for the reader. Okay. All right, so although a basis is defined as a sequence, in other words, technically the order matters, in practice, often we just refer to it as a set. For instance, in this theorem, where we will talk about basis as a subset. Okay. In any vector space, a subset is a basis if and only if each vector in the space can be expressed as a linear combination of elements of the subset in one and only one way. Now, this is the idea of coordinate system. In 3 dimensions, for instance, if I have my ijk, and I have a point in this space, I don't know, I'll just place it here. This point might be equal to the point 1, 2, 3, which is the same as 1 times I plus 2 times j plus 3 times k. And here's the vector associated with that point. Now, there's only one way to express this point, or vector, in terms of I, j, and k. This is the unique expression of that point in terms of these 3 vectors. That's what's talking about here. This vector can be expressed as a linear combination of elements in the basis in one and only one way. Okay? It's a unique coordinate form for the vector in the vector space. Now you can imagine if we threw another vector into this mix and called it L, then we could express this vector 1, 2, 3 in multiple ways as linear combinations of I, j, k, and L. But since we have I, j, and k, which is a linearly independent set and is a minimal spanning set in some sense, there's only one way to express this vector as a linear combination. Right. Now, recall that a subset is a basis. A basis is linearly independent, and it is a spanning set. Right, so recall those 2 properties of basis. I'll just write them down to reinforce. It's linearly independent, and it is spanning. And we want to show that if our set of vectors has both of these properties, then it also has this property, that every vector in the space can be expressed as a linear combination in exactly one way. So let's begin with the proof. All right, so recall that a basis both spans and is linearly independent. The fact that it's a spanning set shows that any vector in the space is a linear combination of these sets in the vector. Okay, so we've shown that every vector in the space can be expressed as a linear combination in at least one way. Now, the theorem says we want to show that any vector can be expressed as exactly one way. So that's what remains to be shown. We need to show that if the spanning set is linearly independent, then the expression of the vector as a linear combination of elements can take place in at most one way. Now, what's the strategy going to be here? Basically, the strategy is, well, suppose there are 2 ways. Suppose there are 2 linear combinations. And then we'll use linear independence to show that these 2 linear combinations must be the same. Okay? So, again, to take a vector in the space, write it in 2 ways as a linear combination, and then we'll use linear independence of the basis to show that, in fact, these 2 linear combinations must be identical. Okay, so let's go ahead with that program. So let's consider two expressions of a vector as a linear combination of members of the subset. Okay, so we've got our fixed basis, beta 1 through beta n, and we're supposing we can express the vector v in two different ways. Now, since they're both expressions of the vector v, we can set them equal. We can rearrange algebraically to obtain this expression. Okay. Now, from this expression, we're going to use the fact that the betas are all linearly independent. The fact that the betas are linearly independent means that in this linear relation, all of the coefficients must be 0. But if all the coefficients are 0, then these two expressions, in fact, are identical expressions. And we don't have two different expressions of the vector as a linear combination. We only have one. So this gives us exactly what we want, that if the betas, that is, the vectors in the basis, are linearly independent, there's only one way to express a vector as a linear combination of these betas. Okay? So we've shown basically that you can express any vector in the vector space in a coordinate fashion with respect to a basis. Okay? So we formalize that with a definition. In a vector space with basis b, remember b is the set of vectors beta that we were just showing, beta 1 up to beta n. Then we call the representation of a vector v with respect to the basis b is the column vector of coefficients in a linear combination. Okay? So in other words, if we have v expressed in this way as a linear combination of betas, then the representation of v with respect to basis b is simply the coefficients in the sum. All right, these are called the coordinates of v with respect to the basis b. Okay, for instance, in the vector space of linear polynomials, we showed that 1 plus x, 1 minus x is a basis of this set. And we computed the coefficients necessary to express a plus bx in terms of these two basis vectors. And here are the coefficients. All right. In this particular example, 3 plus 4x, it can be computed that the coefficients are 7/2 and -1/2. So the representation of 3 plus 4x with respect to this particular basis is given by the two coefficients, 7/2 -1/2. All right, another example with respect to the standard basis. Remember, the standard basis is simply 1, 0, 0, 0, 1, 0, 0, 0, 1. With respect to this standard basis, the coordinates of this vector v are simply the coordinates in the vector itself. So we can say the representation of vector v with respect to the standard basis is equal to the vector itself. And that will be true in general for any n-dimensional vector. Okay, we'll stop here and pick up on the next video talking about dimension.